Okay, welcome Math AI students. Welcome to my first attempt to record a set of notes for you. Make sure that you have downloaded these and print them. If you can't print them, that's fine. You're just going to have to handwrite them. That might be a little bit more work, so if you have any issues, please let me know. But we're going to jump right in. So the date, depending on when you're seeing this, today is that I'm doing it is 8/26/20, but I'm sure that is not the date that you're watching this video. The essential question is, what is special about the sum of an event and its complementary event? Oops, messed up there. Event. All right. So yeah, that's a long EQ. I'm sorry. So the topic today is from chapter 7.1 of the math book you may or may not have right now. I'm not sure if you have it. Of theoretical and experimental probability. So this is an intro to probability, which is going to lead into a lot of our stats stuff. So hopefully I can get through this in 10-ish minutes. We'll see how long it takes. But I'm not going to try to get too wordy for you, but you can pause at any time and look through this or rewind it, and that's the great thing about recording this. So when dealing with probability, we must be very careful with our terms, our verbiage, our words. So be sure that you know these following words. So first off is an experiment. What's an experiment? Well, you probably have an idea what all these words mean. But in mathematics, like in all classes, in all fields, we have very specific definitions. So an experiment, it's a process by which you obtain an observation. So you perform an experiment because you want to see something, you want to see what happens, right? That's the observation. You're seeing what's going to happen. You're observing it. Trials are very closely related to experiment. A trial is when you repeat the experiment over and over and over again. So trials are repeating. Oh, that's not how you spell repeating? Oh no. Sorry about that. Repeating an experiment a number of times. All right. A lot of times it's you decide how many times you want to do the experiment. Like if you want to do 50 trials or 100 trials or whatever it is. An outcome is a possible result of an experiment. That kind of makes sense. That definition kind of fits with whatever you probably already knew about the word outcome. An event is an outcome or set of outcomes. So if you're only going to do one trial, then that was one event, so you only had one outcome. But if you do a series of trials, then the event are all the possible outcomes that have happened. So an event is an outcome or set of outcomes. Okay, so yeah, I can see this might be a little confusing because a lot of these words sound very similar, but I think once you start experimenting with them and actually seeing some examples, it's all kind of fit into place. And then lastly is sample space. Now the phrase sample space is going to come back later on in this unit. A sample space is the set of all the possible outcomes. Everything that could happen in your experiment is considered your sample space. Okay. So it's always denoted by a very special symbol. It's a capital U, but you just can't do this. You just can't put U. You have to put little serifs, and that's why I have a little box here. Serifs is exactly what this little picture says. This is sans serif, like the font you may know. A serif is this tiny little line that you put on all the ends. So there's one here and one here and one here. So sans means without. So sans serifs means a letter that doesn't have those little lines. So you want to draw this little U. Okay, and that denotes the sample space. Now, why do we use a U? It's because the U actually stands for the phrase universal set, but we'll talk about that more later. But I wanted to explain that because it's going to come back. And if I kind of wish we just called it the universal set now, it would make a little bit more sense. All right, so we'll slide down here. All right, so as a lot of you may already know based on what you've experienced in geometry when you learn probability, is that probability is on a spectrum between 0 and 1. all probabilities exist between 0 and 1. And if the probability of something happening is 0, we say that's impossible. If the probability of something is 1, all right, that's certain. That means it has to happen. It will occur. All right. Will we have math tomorrow? Well, depending on what the day it is, it could be possibility of 0 or 1, possible or certain. Now, if something has a probability of 1/2, that's a fair chance. Either it may happen or may not happen. We don't know. It's equal. It's 50-50. We say that it's equally likely. There's lots of different ways to say it. And then, obviously, as you get this way, towards to the right, as you get closer to 1, it's more likely to happen. So it's more likely. I could say it's more likely. And as you go further left, it's less likely. Less likely. Okay, so if you're playing a game and you're trying to win, you probably want a probability to the right of the 1/2. Here in Las Vegas, most games that you would go play on the Strip, I'm going to tell you right now, none of them are all of them are all the way to the left. All of them are all left of this 1/2. None of them are even 1/2. They tend to be far way down in this range, even very, very close to 0. All right. So experimental probability. So we're going to talk about two different types, experimental and theoretical. Experimental probability. So I think I should do an example where you learn some notation and some verbiage. So let's say Colette takes an octahedral die. Octahedral is a fancy word for 8 sides. Octahedral, like an octagon. 8 sides. So you have an 8-sided die. Here's one right here. Got a nice little picture for you. And she designs an experiment. She designs an experiment where she puts it in a cup, shakes it around, and turns the cup upside down to record the result. Because, she's bored. I don't know why she would do this. Colette has completed 50 trials, because obviously she has a lot of free time. 50 trials, just at her house and shaking these things up. She knows the outcome of each trial can be any number from, and now look, now I'm going to use the universal set, and this is some notation. You put the sample space. What are all the possible outcomes? For possible outcomes, are 1, 2, 3, 4, 5, 6, 7, and of course 8. There are 8 possible outcomes. That is her sample space. 1, 2, 3, 4, 5, 6, 7, and 8, the universal set. And the event she's exploring is, so the event that she's looking for is throwing a prime number with an octahedral die. She wants to know what the experimental probability of this happening, which you write this as the set. These are called braces. They kind of look like this. It's kind of hard to see, but they kind of look like this. They're kind of fancy. It took me a long time to learn how to make those. The prime numbers are 2, 3, 5, 7. And of course, if you don't remember, prime numbers are numbers that are only divisible by the number 1 or itself. So for example, 2 can only be divided by 2 other numbers, 1 and 2. 7 can only be divided by 1 and 7. And I should say divided by and get an equal, a solid number answer, a whole number answer. Obviously you can divide 7 by 2 and get 3.5, but that doesn't mean it's prime. So it's 2, 3, 5, and 7. Colette can write this a couple different ways. So some notation that you need to know. You put a capital P, and that stands for probability of, because mathematicians are lazy and don't want to write the full phrase. Probability of, and then you put a parenthesis and you put throw a prime. And for some reason, I already had a little parenthesis right there. So throw a prime, probability of throwing a prime. Or if you decide that, let's get lazy. I don't want to say throw a prime. Let's just call that event A. Event A. You could just say, what's the probability of event A happening? Just as so long as you say that A denotes 2, 3, 5, and 7. Okay? So, this got a little messed up. I am so sorry. We're going to fix that. It says, it is assumed that in many problems that all outcomes are equally likely outcomes. Okay? So, I didn't say that maybe this die here, this die is maybe weighted, so it falls on 7 more than others. We're going to assume it's fair, and there's an equal chance of landing on every side. A fair dice means each side has an equal, equal outcome, has an equal outcome of occurring. Turn that off. All right, I'm sorry I had to take a quick second. I don't know if you heard that. My son was playing very loudly on his Chromebook and making some noise, so I asked him to turn it down. So sorry about that. Okay, so here are the results. Her results are, she has results 1, 2, 3, 4, 5, 6, 7, and 8. The occurrence of 1 happened 9 times. 2 happened 5 times. 3 happened 6 times, and so on. You get the idea. So it might be helpful for us to add this up. It does add up to 50. I know for a fact. She said 50 trials right up here. So it adds up to 50 times. Okay? Thus, the probability of event A was 26 out of 50. Now, where did I get that number? I added all the 2s, all the 3s, the 5s, and of course the 7s. 5 plus 6 plus 8 plus 7, unless I've done my math completely wrong, is 26. This is known as experimental probability. We just performed an experiment to get a probability. AKA, as they like to say, this is also known as the relative frequency of A. All right? That doesn't sound as nice as experimental probability, but you do need to know that essentially these mean the same thing. Okay. Later, you're going to want to go back and annotate these, so this is something that you might want to make a note of. Same meaning. Okay. All right. Well, we're almost done. Let's move on to the next page. Okay. So, slide up here. So, therefore, experimental frequency. I don't know why I wrote frequency. This is an error. I apologize. This is supposed to say probability. Okay, so therefore experimental probability it's a fraction, and on top you always put the frequency of occurrence. This is really wordy. Of event A, in n, I'm going to put n here in parentheses, or quotes, I'm sorry, trials. So n trials is the number of times how many trials you did. And then on the bottom, you just put n. Okay, so it says, let's reflect. What was the value of n in the example with Colette? Well, Colette had 50 trials, so that's her n. And 26 of those trials were event A. So that's where it comes from. I think the example makes a lot more sense than if I had just given you that definition. It's very wordy. All right, so now theoretical probability. Let's not spend too much time on this. It's right today. It's kind of an intro. You're going to get a little bit more next time. So it says theoretical probability allows us to quantify, which means explain with numbers, to convert to numbers, probability without performing many trials or any trials. All right, you don't have to perform a lot of trials. You can just do the math and quantify your probability. So theoretical probability is defined as, let's say, the probability of event A happening equals the number of times A occurs over the number of elements, the number of outcomes in the universal set. Again, I'm being sarcastic here. It says, now you know everything you need. No, not really. Let's explain this really quick. This looks confusing, but if you understand the symbols, it really clears things up. And I think that's the problem with mathematics a lot, is that I guarantee you understand the math. It's the symbols that are just throwing you for a loop. The symbols make things confusing. So N of A, or NA, is the number of outcomes for event A. All right, it's the number of times A occurred. The number of times A occurred. In fact, I'm not going to write that, but if you wanted to annotate this later, that would be a fantastic thing for you to write over here, over on the left. It's the number of times A occurs. And then U, the universal set, it's the number of outcomes in the sample space. It's the number of possible things that can happen. Okay? So this means the theoretical probability of getting a prime number in Colette's experiment we can write this, we can say that, that would be probability of A equals, there are only, if you remember, 8 things that can occur. She could get a 1, 2, 3, 4, 5, 6, 7, or an 8. And of the prime numbers were 2, 3, 5, and 7. There's only 4 prime numbers. So her theoretical probability was 4 out of 8. So you would assume that for every 8 rolls, maybe 4 of them would be prime numbers, but that's just in theory, it's theoretical. Obviously, when the experiment happened, that didn't happen. We actually got a little bit more than 4 out of 8. We got 26 out of 50. That's over half. So let's reflect. Why did the results in the experiment not match the theoretical results? I don't want to write this right now. I think this is a question that you should think about and ask. Why did the results of the experiment not match the theoretical results? So I'm going to leave that for you to reflect on. And this would be something fantastic that we can talk about in class when you come back. Now, one more thing before we get out of here. Actually, kind of 2 little things. The complement of event A. The complement. And I don't mean complement as in, hey, I like your shoes. No. That's different. Complement of event A. Ran out of space there. Denoted as, and denoted means like written as A, and then it looks like this little prime mark for those of you who remember in geometry. All right, that means the complement of A is the probability that event A does not happen. All right, so what is the probability of the complement of A in this above example with Colette? Well, it's not too special. If there's a 4 out of 8 chance that A occurs, that means that it doesn't occur is also 4 out of 8. Well, so 50-50. Not too special, but which is why I have a little, let's reflect. It says let's reflect. If event B is rolling a 5 or less, then find B, a complement of B. I'm going to let you do that. I'm going to let you think about that for a moment. So rolling a 5 or less on the octahedral die. Okay, think about that. You might even want to flip it over and look at it. And I'll let you figure that out, and maybe we can discuss it when you come back into class. So now expected value. So if there are 100, expected value is just that. What value can you expect to occur? So if there are 128 students in a classroom, and the probability of being absent is 1/10, 0.1, or written as a fraction, 1/10, then how many students can you expect to be absent? Well, to do that, this is just finding a percentage of a number. I'm going to multiply 128 times 0.1, and I get 12.8 kids. Well, this is a perfect example of where mathematics is perfect on paper, but not perfect in real life. I can't have 12 students absent and then 8/10 of one absent. What does it mean? Their left leg comes to school? You can't have that. So we're going to say between 12 and 13. I mean, you can round up to 13 students. That would be acceptable. But you could also say, or between 12 and 13 students can be expected to be absent. All right. So expected value is just that you use the probability to maybe foresee and predict what's going to happen. Does that mean it has to happen? No, absolutely not. We can't predict the future, but we would not be surprised if 12 or 13 students were absent. All right. So practice problems. There's some practice problems right here. I'm going to do. I don't want to do 1 and 2 right now. I don't want to do 1 and 2. I'd really like you to attempt 1 and 2. Let's talk about 4. I'm going to leave you actually to do 1, 2, and 3. I think these are great practice questions. Work on them. That'll be part of your homework, and then we can discuss them when you get to class. So let me grab a different pen here. It says, what is the probability of throwing a factor of 24 on a 4-sided die? Well, I assume that my 4-sided die, the universal set, would be, that is a horrible brace, I'm very sorry, 1, 2, 3, and 4. Okay, 1, 2, 3, and 4. Now, a factor is a number that can be that 24 can be divided by. So 24 can be divided by 1, 2, 3, and 4. So what's the probability of me throwing a dice and getting a number that's a factor of 24? Well, it looks like it's going to be what's the probability of throwing? It's going to be a 100% chance, right? Probability. Or if I throw this, it'll be 4 out of 4 because there's 4 different things that can happen, and 4 of those events are true. They work. So 4 out of 4. So it is a certain possibility of it occurring. All right. So that's it. You'll be responsible for answering some of the questions I didn't, along with the practice questions, and then completing the summary. I hope that helped. If I made an error, I apologize. We can most definitely fix that in class, and I will see you then. Thank you very much.